All right, continuing on in Chapter 5 in Section 5.4, the title of this section is Working with Integrals. So let's do some review from algebra. There are functions out there that are called even functions. Algebraically, you know you have an even function if when you evaluate f of negative x, you get the original function back. So f of negative x is equal to f of x. Graphically, an even function is symmetric about the y-axis. So here's the graph of an even function. Don't know what the even function is, but it's symmetric about the y-axis. So this means that when we integrate from negative a to a, f of x dx, since it's symmetric about the y-axis, this region over here, that's below the graph of f, above the x-axis, between negative a and a, the area of that region, well, because of symmetry, it should be nothing more than 2 times the integral from 0 to a, f of x dx. So with an even function, you can just immediately rewrite it like that, and that's pretty cool. Now we have these things called odd functions that you would have seen in college algebra. Algebraically, you know you have an odd function if when you do the f of negative x, you get the opposite of the function. And graphically, an odd function is symmetric about the origin. So let's look at the graph of an odd function that's symmetric about the origin. So it looks to me that with an odd function, when you integrate from negative a to a, you're going to get a value of 0. And that's because you have symmetry about the origin. So if you wanted to find the area, it's almost like this region here, because it's below the x-axis, you could think of it as having a negative value. This region has a positive value, but because you have symmetry about the origin, the magnitude of this region is the same as the magnitude of this region. So when you add them together, this is positive, this is negative, magnitudes are the same, they would cancel out and equal 0. I'm going to put this into a theorem. A is a positive real number and f is an integrable function on negative a to a. So notice we're talking about an interval that is symmetric about the y-axis. If your function f is an even function, then the integral from negative a to a of f of x dx is equal to 2 times the integral 0 to a f of x dx. And sometimes that's a nice thing to do with an even function because sometimes it's nice to have 0 as one of your limits of integration. Likewise, if f is an odd function, then the integral from negative a to a of f of x dx is 0. So I'm just going to, in this example, write it down because I'm going to the chalkboard. I'm just going to attack this one example, trying to use these properties you see in the theorem. And that's the whole point of doing this example. So please write this example down because I'm heading off to the chalkboard to do it. All right, folks, this example we're asked to evaluate the integral from negative 3 to 3 of x squared minus x cubed dx. Now I realize I could just get the antiderivative and crank it through the fundamental theorem of calculus, but the point of this example is to practice even and odd functions. Going forward, trust me, especially recognizing even functions can be beneficial. So that's what I'm going to practice here. First off, the interval negative 3 to 3. Notice that interval is symmetric about 0. So I'm going to split this into 2 integrals. And now I'll make the following claim. X cubed, that is an odd function. So on the interval negative 3 to 3, because it's an odd function, this integral has a value of 0. x squared is an even function. So I can rewrite this, integrating negative 3 to 3x squared dx, I can rewrite it as 2 times the integral from 0 to 3x squared dx. And I've already said that is 0. See, a lot of times it's nice if we can get 0 as one of the limits of integration. It helps on the evaluation of the fundamental theorem of calculus. So, continuing, we get an antiderivative. The antiderivative is 1/3 x cubed. Evaluated from 0 to 3. So when 3 comes in for the x, see 3 cubed is 27. 1/3 times 27 is 9. 2 times 9 is 18. And then when 0 goes in for the x, you end up with 0. So definite integral has a value of 18. So just to practice this even-odd function idea, I have a couple here I'd like you to try. So in the section 5.4 exercises, I want you to try numbers 12 and 14. And you know the drill. Pause the video, do numbers 12 and 14, and when you're done with them, restart the video, and I'll be here at the board making sure you have correct answers. All right, let's see how you did in doing numbers 12 and 14. So number 12, integrate from negative 200 to 200, 2x to the fifth. Well, 2x to the fifth, it is an odd function. So since we have an odd function on the interval negative 200 to 200, the value of this definite integral is 0. That was pretty quick. Number 14, integrating from negative pi over 4 to pi over 4, cosine x dx. Well, cosine is an even function. So since it's an even function, I can rewrite the integral as 2 times the integral from 0 to pi over 4, cosine x dx. Get my antiderivative. Antiderivative of cosine is sine. And so now we're just left with doing 2 times the sine of pi over 4 minus 2 times the sine of 0. And this is friendly because the sine of 0 is 0. So that is just 0. So we have 2. From the unit circle, we know the sine of pi over 4 is square root 2 over 2, which I would simplify that down to just square root 2. So, folks, hopefully you got 12 and 14. Let's head back to the slides to see what's next on working with integrals. All right, so even and odd functions can make our life a little easier. Okay, now we're going to look at, I just think this is a really, really cool thing. Look at this figure to the right. So here's the graph of some function. I don't know what the function is. I don't care. What I'm trying to show here in this figure is that the area of this red rectangle, that one rectangle, is the exact same as the area under the graph of f of x above the x-axis from A to B. So I'm saying the area of the red rectangle is the same area as the area of the region that's below the graph of f above the x-axis between A and B. Well, let's look at the area of the red rectangle. How would I find the area of the red rectangle? Well, I know it's the base of the rectangle, which that base would be B minus A, times the height of the rectangle. The height of this rectangle is f of c. How am I going to find the area under the curve? Well, that's the definite integral, a to b, f of x dx. So the area of the red rectangle, which is f of c times b minus a, equals the area under the curve, which is the integral from a to b, f of x dx. And this is actually called the mean value theorem for integrals. And there's something that's going to be really cool about this. So if your function's continuous on closed interval AB, then there's a number C in the closed interval AB such that the integral from a to b f of x dx is equal to f of c times b minus a. So it's saying, there's, area of a rectangle equals area under the curve, which that's cool in and of itself, but there's something really neat about this value here, f of c. That value, f of c, in the mean value theorem, it has a special name. It's called the average value of f on closed interval AB. So we can determine the average value by simply doing 1 over b minus a times the integral a to b f of x dx. So it's kind of like in the mean value theorem, if you solve for f of c, you divide both sides by b minus a, and this is what you get, 1 over b minus a times the integral a to b f of x dx. And here's what I think is really, really cool about this average value. You could think the average value, it's basically like finding the average of all the y's. So all those points that are on the interval, you're finding the average of all the y coordinates. And there's an infinite number of them. That's what the average value is exactly like. And that's kind of cool. And some people like to think that the integral from a to b f of x dx is analogous to giving a total and then dividing by b minus a, the length of the interval, or multiplying by 1 over b minus a. That's how you get the average. Because then it kind of reminds you of how you find the average of, say, 3 test scores. Let's do a quick example here. Got the function cosine x on the closed interval 0 to pi over 2. We're going to find the average value on the interval 0 to pi over 2. And then in part B, we're going to determine all values of x in that interval for which the function equals its average value. So this is going to review inverse trig, which is something that's coming up in the next chapter. So let's make sure you have this written down, because I'm heading off to the chalkboard to do both parts of this example. All right, we've seen the mean value theorem for integrals. So this example, we were given the function f of x equals cosine x on the interval 0 to pi over 2. And in part A, we're asked to determine the average value of the function on the interval 0 to pi over 2. So to get the average value, it's 1 over b minus a, integral from a to b, f of x dx. All right, so out front here, we know pi over 2 minus 0 is pi over 2. And I'm going to go one more step. 1 over pi over 2, that can simplify to 2 over pi. So now we just need to get the antiderivative. And the antiderivative of cosine is sine. Evaluate that from 0 to pi over 2. So we have 2 over pi sine pi over 2 minus 2 over pi sine of 0. We know sine of 0 is 0. Sine of pi over 2 is 1. So the average value is 2 over pi. Part B, determine all values of x in the interval 0 to pi over 2 where the function equals its average value. With just a direct interpretation, a direct translation of the English into math, where the function, the function is cosine x, equals, well, that's the equal sign, its average value. Its average value is 2 over pi. All right, now I know on the unit circle, cosine matches up with an x-coordinate, but I don't know the x-coordinate that is 2 over pi. If this were a 1/2, I would definitely know where we're at on the unit circle, but it's not. It's a 2 over pi. So for that reason, I need to use inverse cosine. We will do the calculus of the inverse trig functions in the next chapter, but cosine x equals 2 over pi means to get this value of x, we have to evaluate inverse cosine of 2 over pi. And, you know, that's like the exact value for x. But if we use our calculator and we get a decimal approximation here, we're going to get x is about 0.8807. And, you know, that's it for this example. So I'd like you to practice a couple in the section 5.4 exercises. Numbers 29 and 40. You need the result of 29 to do 40. And 29, you know, it's the same function, it's just a different interval for the function. I'll give you a hint on number 40, because in number 40 you're finding, you know, the values where the function equals its average value. You should get two values of x in number 40. So go to the 5.4 exercises, do 29 and 40. When you're done, you know, pause the video as you do it. When you're done, restart the video and I'll be here at the board working through them. Alright, number 29, you were asked to find the average value of f of x equals cosine x on the interval negative pi over 2 to pi over 2. So that starts off 1 over b minus a integral negative pi over 2 to pi over 2 cosine x dx. So folks, when you do this, pi over 2 minus negative pi over 2, that's pi over 2 plus pi over 2. That gives you 2 pi over 2. Well, 2 pi over 2 is just pi. So we have 1 over pi, the integral negative pi over 2 to pi over 2, cosine x dx. And now I'm going to make use of the fact that cosine is an even function, and so I'm going to rewrite this. I'm going to pull a 2 out front. 1 over pi times 2 is 2 over pi, and just integrate from 0 to pi over 2. So we get 2 over pi, antiderivative of cosine is sine x, evaluated from 0 to pi over 2. So we get 2 over pi sine pi over 2 minus 2 over pi sine 0. We know that's 0. This is 1. So we get the average value of cosine x on the interval negative pi over 2 to pi over 2 to be 2 pi, or 2 over pi. Excuse me. Number 40. Well, where does the function f of x equals cosine x equal its average value? Looks an awful lot like the example we did, but I told you there would be, I think I gave you the hint that there were two values of x here. So, you know, we have right now x is, use your calculator, you get what, 0.8807. But here's what we need to remember. You know, let me get this yellow chalk here. You need to remember we're on the interval negative pi over 2 to pi over 2. So on the unit circle, that would be the right half of the unit circle, because down here is negative pi over 2 to pi over 2. Again, remember that this is an x coordinate on the unit circle. I mean, it's about what? I mean, 2/3. It's an x value of about 2/3. So it's I'm just going to arbitrarily say that point's about right there. The x coordinate is 2 over pi. I don't know what the y coordinate is. I don't care. Right now we know this angle here is 0.8807. That's what the calculator told us. But notice there is another point on the unit circle, on the right half of the unit circle, that has that same x coordinate of 2 over pi. It would be right here. And again, I don't know what the y coordinate is. So this angle here, this is the other value of x that we need to determine. No matter how many times you keep doing inverse cosine of 2 over pi, it's not going to tell you this angle. It's only going to tell you the point 8807. Well, one of the beauties about the unit circle is the unit circle has a lot of symmetries. It's symmetry about the x-axis, symmetry about the y-axis, symmetry about the origin. So since these 2 points have the same x-coordinate, and I know this angle here is 0.8807, this angle here has to have the same magnitude of that angle. It has to have the same magnitude, but notice the rotation it has. That kind of rotation, remember that kind of rotation? A clockwise rotation means the angle is negative. Those are the 2 values of x in the interval negative pi over 2 to pi over 2, where the function cosine x is equal to its average value. And what I really liked about 40 was it allowed us to review a little bit of inverse trig, the unit circle. I mean, inverse trig functions are looming on the horizon, coming up in the next chapter. But folks, that's it for section 5.4. So at this time, head off, do the exercises in section 5.4, and thanks for watching.